So let's take a look at some relatively simple examples. So this one says the radioactive decay of iodide 131 has a rate constant of 0.138 inverse days. What is the half-life? Well, we know our equation T1/2 is equal to 0.693 over K for any first order rate law, and we're assuming this one's first order. I guess I should have said that in the question, whatever. What we want is T1/2. We're given the rate constant of 0.138 inverse days. That goes into K. So we simply just plug that into there and then do the math. And what you end up with is 5.02 days. So every 5.02 days, the concentration gets halved. And so let's use this information for another question. So this question is, how many days until 12.5% of the original concentration is left? Well, if we think about what a half-life is, it's after each half-life, the concentration is half of what it previously was. So if we start off with kind of 100% of the original, after one half-life, we'll end up with 50%. After another half-life, we'll end up with 25%. And then one more half-life, we'll end up with 12.5%. So you can see this took us 1, 2, 3 half-lives to get to the targeted date, right? And so we have 3 half-lives. And then from our previous question, we know each half-life is 5.02 days. And remember, for our first order, our half-life doesn't change. It's always the same. And so we just multiply these two and you get 15.06 days, right? So that's how long it's going to take. So that was pretty easy because this question was asking something that's nice and kind of divisible by 1/2, but that's not always going to be the question. How about until 30% is left? And so we can see that somewhere between 1 half-life and 2 half-lives, but we can't actually tell exactly where because this is non-linear. And so what we have to do here is use a separate equation. So the equation for any order half-life is going to be the concentration of A at time t is going to be 1/2 to the n times the initial concentration, where this 1/2 or this n value here is the number of half-lives. And so, right, we want to know how much until 30% is left. And so we can plug that into here. And then the other trick here is to know that if 30% is left, then 100% was originally there. And so you can plug these in as decimals or percents. It doesn't matter. I just usually do decimals. So 0.3 is equal to 1/2 to the n times 1, right? That's 100%. And so then we can reorganize this equation to get 2 to the n is 0.3. And then we have to solve for our n. So think back to, I think, earlier in the chapter, how are we going to do this? We're going to take the log of both sides. Because remember, the log of a to the x is equal to x log of a. So that's how we're going to solve for our n. So we get the log of 2 to the n is equal to the log of 0.3. We can pull this n out front. And so we get n log 2 is equal to log of 0.3. Divide both sides by log 2, and then you get n is equal to log of 0.3 over log of 2, which is then equal to 1.74. Right, 1.74. And remember, this is the number of half-lives. So this is how many half-lives it took us. But the question asked is how much time passed, not how many half-lives, but how much time. So again, we know that each half-life is this 5.02 days. And so we can just take these two numbers and multiply them. So you can use this equation up here for any order of rate law to solve for how many half-lives are remaining, but then this next step can only be done for first order because only first order half-lives stay the same throughout. We'll see in the second and the zero order, the first half-life is either longer or shorter than the following half-lives. So anyways, 1.74 times our 5.02, we end up with 8.73 days.